Hello, my name is Marc Hanheide, and welcome to my talk on autonomous robots supporting software production. There are many challenges these days in software production, particularly we're looking here at strawberries. There's a strong reliance on manual labor due to quite complex operations, especially in picking, and we've seen more and more shrinking of workforce, a lot to social political pressures and an aging population. But there's also a lot of these political pressures here in the UK, obviously. Brexit shall be named as one of them. But in general, there's a tendency to rely less on foreign labour to come in, and with the high wages here, there's a strong drive at the moment for automation, in particular in software production, which are quite high value crops. So we're here looking particularly at systems that support the growth of strawberries on tabletops, as you see here on the right hand side, where the strawberries are raised off the ground and provide high productivity in growing on those tabletops. The robots we're using here in many different applications is the Saga Robotics Thorvald platform, which is a modular mobile robot platform. Comes in different shapes and forms that can be customized depending on the operations and on the tasks you want the robot to perform. So we have a really big project here covering different aspects of a fully autonomous farm. So starting off from crop care, monitoring of crops, over supporting picking, supporting transportation, and crop care also in the context of providing UV treatment against powdery mildew, for instance. So many different applications that we facilitate through this platform, and we're working very closely with our colleagues from Saga on many different applications. Now, in this talk I will focus very much on the picking operations, and we will have two main parts of that. One is the actual transportation, and then I'm going to just briefly hit on the current results that we have got for autonomous picking. We have our own little strawberry farm on the University of Lincoln in our Rice Home campus. This is something that we've been running for now the third year, so we actually produce strawberries that are ready for the market. We sell them locally. Yeah, and this is our test environment. It's really helpful to get out of the labs and try these things out in reality. One of the aspects here is, of course, that we don't just stick to this relatively small farm here. We have 2 tunnels of strawberries around 35 meters long. We also test these systems on the real farms where we have up to 50 tunnels up to like 200 meters long. So that's our real test environment. But as a kind of development side, it's pretty brilliant that we've got this one on site here. So this is all part of what we call the RASberry program. This is the sort of big vision of providing automation on strawberry production. Part of that is the hardware development, developing these robots further, managing an entire fleet of different robots doing different tasks, solving the problems that come with mapping these environments with the navigation in there, and really long-term autonomous operations is one of those key requirements here. Our partners are currently deploying already UV treatment, as I said, against powdery mildew on the large scale, on a commercial scale, on farms in Kent in the south of the UK. And therefore, we need to really have a reliable navigation system that these robots can cover kilometers every night when they deploy these sort of treatments. Obviously, we also have humans in these environments. We will come later to the point of supporting human fruit pickers with transportation tasks, and the perception that we need to be able to detect and reliably localize strawberries in order to pick them is one of the key bits in here. And obviously the kind of overall grail is to have an integrated system that can monitor these crops, can deliver treatments to them, that is then also able to pick them autonomously and transport them to what we can call a cold storage. So really kind of an integrated program with many different aspects, and I'm making references to a couple of papers as I can only scratch on the surface here for most of these things. So, as I said, the key aspects here that we're going to discuss is the field logistics and the autonomy of these robots as they're out in the fields. I'm not going to talk much about the perception side, as my colleague Dr. Greg Cherniak is going to present that in a different presentation, and I'm going to just briefly touch on the current status of our autonomous picking solutions that we've got in here. So let's start and look at the transportation. Now, what we have is a general kind of quite reliable autonomy, as we said before, for these robots, that they cover kilometers every night or completely on their own. Relatively standard, I would say, to a large extent. So we use hybrid GPS and laser-based navigation, RTK GPS for quite high localization precision. But this is sometimes quite tricky, especially in these tunnels where we've got these metal beams. So the localization itself in those environments isn't necessarily up to the high standard you'd want. And so we have combined this with laser-based navigation using lidars and mounted on the robots also for safety, and have also developed special navigation modes for in-road navigation, exploiting these sort of poles that you've got in these tunnels. And then we've got some papers also on automated tuning of navigation parameters through some genetic algorithms to actually have a very smooth and reliable motion with these sort of navigation components that we have developed. So I'm going to refer you just to these related papers that could be of interest to some of you. In-field logistics. So is that kind of the low-hanging fruit, we could say? Because we see that human pickers are very, very good. They're very dexterous in their manipulations. They're super fast at the moment. But what we've also discovered is that they spend around 20% of the time transporting fruits from the point where they're picking them all along these very long tunnels to put them onto some trolley to drop them off. So one easy thing possibly to do is to actually just automate the transportation and develop systems for in-field logistics. In order to be really useful, here we have the challenge that we need to send the robots to the right place, close to the picker, so that they can receive the crates when they have filled a crate full of strawberries. That we allocate the right robot to serve this. So if we've got a fleet, it's the question of which one should actually serve and go to one picker, and the question also of navigation here. So how do we avoid congestions if we've got several people on this farm? So here's a prototype of our smart trolley, as we call it. So pickers can call a robot to receive produce from them, and then they move along. These robots move along, drive up to the picker that has called them, receives that produce from them, and then drive autonomously off to the drop-off zone here. And obviously here, to serve a real farm, we need a larger fleet of robots that serve these transportation tasks, and we need to be able to also very precisely know where the people are. That is, on the one hand, to drive up to the right person, and at the other hand, we need to be able to also avoid other pickers that may be in other rows in between, so to avoid going into rows that are currently already occupied. And for this, we have designed this this so-called smart trolley system that we've had. We had one system that was based on mobile phones, and another one that is this kind of embedded system, which is relatively low cost, has a low cost GPS for tracking in here, and also kind of low computational power. It's quite cheap to put into kind of mass production to put on these smart trolleys. Now, the challenge for that is obviously to know where these people are, and as I said, this is relatively low cost GPS, so we don't get the exact precision that we have for our robots, where we can afford quite expensive RTK GPS systems because there's fewer robots, but we will have many of those small units to track these pickers. So what we've looked at here is to actually exploit that we have topological constraints. Pickers will always travel along rows and they won't jump between rows, so we can easily integrate all the many readings we get over time from the GPS system from these smart trolleys and overcome the very noisy measurement. So if you see this, these rows are roughly 1 meter apart, but the GPS noise, the kind of localization noise we get from the system is much greater. We've got up to 3 meters here. That could be even worse when we've got these tunnels with these metal beams in there. So what we've done here is we designed what we call a Bayesian filter, topological particle filter here, and we take these topological nodes that we've got, we know the layout of the farm, and then take these GNSS readings as the observations. So it's kind of standard localization methodology particle filter, if you want, that is known in robots. Here we use it to track the localization of the human pickers, of these smart trolleys that you see here, which are connected to these devices. So how do we do that? Relatively straightforward. So we have a topological map, a set of nodes and edges, and this is already known by the robots because it's part of the overall deployment of these robots onto the farm. We have these nodes roughly about 4 meters apart, 3 to 4 meters apart along these rows, and we know exactly which are the routes we can travel. And with that in place, we can design a topological particle filter where we basically just start with overall initialization of where these pickers are, and then we can predict the future state of particles from knowing how these people can move based along this topology. So basically just saying which node they're in. And we use a continuous time model here, where we assume that people are moving at a certain rate along. When they are picking, they have a relatively constant rate that they're moving along with, so we can even anticipate and predict where they are in the absence of some readings for some time. So this is to overcome any problems that we may have, because the readings from the GPS may be quite sparse in time. So with that system, we are able actually to this kind of shows you some results of this. We are able to very precisely predict which particular node a picker will be at, even if we have only spurious readings from GPS and they may be quite noisy. So it's this integration and this kind of integration with the topology that allows us to be quite precise about the node that a human will be at. And it's quite important for us to get that right, because if the robot enters another row, that row may well be 200 meters long and we're going to go in the wrong one, and it's of no use at all. So that's the way how we solve the picker location problem. With that comes then that we have also a coordination system. So once we know where these people are and when they know when they call a robot over, we need to coordinate the overall fleet. Right? So we have already tried some different tests here with what we call discrete events simulations. Do some general tests, find the sweet spot of how many robots you need for how many pickers, depending on the topology of a farm. And then we know exactly, if we have these many robots, how do we allocate the tasks to them, and how we find out which robot should go which route to best reach the picker that has actually called for it. So some ideas here around how this works. So we have a system that is scalable to relatively large fleets, so 50 plus. We use a centralized auction-based task allocation system in working with our colleagues at the University of Oxford here, and there we learn about routes that may be blocked for some time and not be able to traverse them quickly. So we have a probabilistic congestion-aware route planning that then decides which routes to take depending on the occupancy, whether there's a picker there or another robot that may already get into its way. So that's just a kind of quick run through how this overall system works. Obviously the ultimate aim here is to not only support human pickers, but even if we have autonomous picking, we need the logistics system still to have robots be sent over, retrieve the fruit, because you don't want robots that are picking to then spend a lot of time to travel down again. So we're working on actually handing over from picking to the logistics system as well. Now, I'm going to just give you a quick run through some of the picking solution we have developed so far. This gives you a quick idea of how this works. So we have a perception system here based on convolutional neural networks that is very good at determining whether a strawberry is ripe or not ripe and finding its exact location, and combining depth and RGB information here, we are able to detect these strawberries quite accurately. And then it's a question of path planning. So how do you actually pick this particular strawberry? We've got a standard baseline path planning system already implemented. That's what you see here. So this is basically getting the fruit with some constraints, planning a path with our system that you see here. So this is the current picking system that directly picks into a punnet, as you can see from this video here. And we also have a digital twin to facilitate the development of these sort of systems. More advanced, the stuff that we're doing at research at the moment is to actually use probabilistic motion primitives to deal with clusters, where you don't just go straight for a strawberry, but you actually take the surrounding into account and find a trajectory that can allow the picking head to wiggle into place here. So that is really cutting edge stuff at the moment. We're going to present that at IROS, and there will be some updates on that coming soon to get that integrated. So just as I don't have much more time, a quick summary and some outlook into some future work. So we really have this overall program of different tasks that are done with autonomous robots to support soft fruit production here. Various applications. We've seen the in-field logistics. You've probably seen some of the fruit picking. We're also using this to plant care, UV treatment. We're working currently also on a spraying application where these robots can go out and spray the fruits, and also do yield prediction and crop monitoring. So it really is an integrated challenge with logistics that is still needed after picking, even if we do it autonomously. At the moment, the kind of immediate goal is to support fruit pickers on the way towards this kind of full automation. That's the ultimate aim. Thank you very much.